program scientists of the VLT, the principal job of the program scientist is to make sure that the VLT program, in this case, is up to date, in the sense that the instrumentation and the telescopes and the data reduction facilities and everything else is solving the scientific problems that are important today, and that we are planning for the future to solve the scientific problems that will come up in the next decade or 2 decades. So I began in 2004, and then one of the big problems that we saw were coming up was a search for, well, we had already found planets, and planets were ongoing. We had the instrumentation, but then we wanted to take spectra of the planet atmospheres and find out whether planets have life. So that was the thing that we were planning in those days. And then I became interested in figuring out, well, what's the probability that there is life in other parts of our galaxy, intelligent life. And this is the famous Drake equation that you know, and it's one of the easy ways in which one can scientifically answer the question, well, how many, or are we alone in the universe, or are we alone in the galaxy? And you just compute this number by multiplying all of these fractions. This is sort of the basic text of astrobiology, right? We want to know this. By the time I was looking into this, these terms, what's the probability of finding life on a planet, and if you find life, what's the probability that it will turn into intelligence, and blah, 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 were the subjects of interest. And the last number here is, how long does an intelligent, civilized, advanced civilization last? This is what's called the longevity. How long does an advanced civilization last? So anyway, so this I became interested in figuring out what is this number in order to calculate this whole product. And I predicted then that by 2020 we would have found the first planets with life. So I'm running out of time. That was the prediction then. So there's a question: how long does this technological civilization last? L, right? And so this is like the joke that the 4 cardinal points in Chile are 3, north and south. The 3 main challenges that threaten our civilization are 4. Impacts of comets and meteorites, climate change, wars, and now a 4th has appeared, which I added recently, this artificial intelligence. There are people saying that artificial intelligence may threaten our civilization. So I started looking into these issues here, and that's what brought me into climate change. So, well, this is just a graph showing the great extinctions that have happened in the past, in the history of Earth, and these are the geological periods and when they happen. And the causes of this have generally been climate change, volcanoes, and meteorites impacts. Okay, so it's relevant. And people say that now the current era that we are living now is called the Anthropocene, and that we are witnessing, as of today, the extinction of enormous numbers of species. And there's this book by Elizabeth Colbert that says the natural extinction rate is from 1 to 5 per year, and the current extinction rate is between 1,000 and 5,000 species per year. So that's where this comes from. Just okay. Now, the people that deny climate change say, "Well, climate change," and you hear that, and you hear that really by people have channels in YouTube and they give talks and they appear in talk shows and says the climate has always changed on Earth, which is true. And so what's happening now is just natural. It will go back to normal without us having to do nothing. And that is illustrated here. This is the weather bulletin for the past 5.5 million years. And you can see this is the temperature. And this is the isotopic ratio that is used to estimate this temperature. This comes from the little shells of microorganisms on Earth. Oh, sorry, on the ocean. And these are the last two geological periods. The Pliocene, which means the late new, and Pleistocene, that means the real late new. So all of this geologists always use this ending "cene" to characterize their timing vocabulary, and "cene" means new. And what is new is that you see how the weather was changing. It was pretty warm, but it's always changing. This is temperature here. From 0 is our current temperature now on Earth, the average, and it's always changed. However, at the beginning of the Pleistocene, something strange happened. The Earth that was slowly cooling began to have these big oscillations in the climate, big oscillations that happen every 41,000 years. We will come back to this 41,000 years. And why did this happen? We are not really sure, but the most likely explanation for this is that the drift of continents finished around this time. All the continents came to the position that we see them now. The isthmus of Panama came up, interrupting the circulation of currents in the ocean, and this caused the climate to change. But then about a million years ago, it went from the 41,000 period oscillation to even bigger oscillations that happen every 100,000 years. Okay, this is about a million years ago. This transition took place. Now, this period, when the oscillations became very deep and the temperature, as you can see in the plot, went down by minus even 10 degrees. It went really down in each of these cycles. These cycles are called the ice ages. And this is a photograph of Antarctica. And if we look at Antarctica, this is a hotel in Antarctica. There are hotels in Antarctica. Antarctica is a continent. You see now in the coastal regions of Antarctica, you can still see the continent. And on top of the continent, there is a massive amount of ice, kilometers and kilometers of ice. And it's very abrupt. You come, as you go from the coast towards the plateau, you run into this wall of ice. Now, as it turns out, the history of the Earth's climate is recorded in this ice. And here are various places on Antarctica. Antarctica is sort of a very gentle, hilly, the ice part of Antarctica is a gentle, hilly surface covered completely with ice. And the thickness of the ice, there are some boulders or mountains, you could call them. They're called actually domes because they're so soft. The thickest ice is the Dome A. which is somewhere here, and Domei is 4,093 meters above sea level. It is currently the site of a Chinese research station in Domei. Then there is Dome F somewhere. We'll find it one day. This is Dome Fuji, Japanese. Vostok, Russian, 3,528. And then Dome C, where the Epica, this is the Italian-French station, is located. The South Pole is here and is 2,771 meters above sea level. So the whole of Antarctica is pretty high. Now, how is the weather, the weather history recorded on the ice? Well, it happens as this. It snows. The snows drags with it air from the atmosphere and traps it in this layer of snow that then becomes ice. Then the next year, another snow comes, another snow, and eventually this whole mountain of ice has accumulated, and in it are little pieces, little particles, little globules of atmosphere of those days. So this is a core, an ice core that they extracted in Vostok, and they could read the climate, the history climate of the last 420,000 years in Vostok. This is a team, this is a core, and then they stopped when they reached 420 years, which is 3,623 meters, because they discovered that there was a lake here. And they didn't want to contaminate this lake with, it was supposed to be a pristine lake, and they didn't not want to contaminate it with the equipment, so they stopped. But already you see this area here was already transformed, so they could only reach 420,000 years. And this is a sample of one of the cores, and this is what they were extracting from there: microbes and other things. Okay. So this motivated this French-Italian station to experiment to go and core the ice at Dome C. And here it is in 2004. They reached 3,270 meters. And they were able then to record the weather, the history of the climate in the last 800,000 years. And what did they find? This is what they found. These plots will keep coming back. We have time running from right to left. So here's now, here's 400,000 years ago. This is the depth of the ice. The red curve is the temperature. The blue curve is the CO2. The green curve here is methane, and this is again an isotopic ratio that is more technical and doesn't concern us today. Now, so this is what they found. They found that between the ice ages, the glacier periods, that lasts, each of them lasts about 100,000 years. There is an interglacier where the temperature goes up. It goes up by, as we saw, about 10 degrees. But in between, there's also a lot of variation. So in that sense, the Earth's climate has never been stable. It's always changed. But the most dramatic changes are the 100,000 year period of the glaciations. Now, let's focus on the last ice age. The last ice age is this one. Remember, this runs inverted. These are now the Epica data, not the Vostok data. And it's the temperature again. And the last ice age started around 110,000 years ago. Here it is. And then ran until approximately 18,000 years ago, where is the end of the ice age. And then the temperature rose sharply with some features, and this is now called the long summer, which is the summer that we're living now, and this is the title of a book that explores the effect of climate in modern times. So astronomy, it turns out that astronomy plays a critical role in understanding why climate, the natural causes of climate change. And we see here some of them. We have astronomical, we have the sun. The sun sometimes decides that it will stop making spots and solar activity dies down. The solar constant gets a little bit smaller. The temperature doesn't change, but the amount of light it puts out gets a little bit smaller, and that's enough to change the climate. What does astronomy has astronomy to do with the climate? What the most obvious example that we all know is the seasons. The seasons are due to the inclination of the axis of rotation of the Earth, right? So the sunlight arrives inclined to the Earth, and that causes the seasons. But it turns out that there is another variable, and it's the ellipticity of the orbit of the Earth. This is a very exaggerated drawing just to show the effect of ellipticity. The Earth goes faster, right? Remember Kepler's law, when it comes closer to the sun, and slower when it goes over there. And if you put at a single place on Earth anywhere, and you take a picture of the sun every day at the same time, you see that the sun describes a figure like this, which is due to partly to the change in speed and partly to the fact that the orbit is inclined. The rotation axis is inclined. Now, the rotation axis of the Earth is not fixed in space, but it precesses. It does like this, precesses, and it also nutates. So it does like this as it precesses. And this nutation and precession, together with the ellipticity of the orbit, are the three parameters that have to do with the weather. With the climate. Now here's an interlude for Olavistas. The zodiac is, in fact, a calendar. I don't think I need to go into this subject here, but it is a calendar. Okay. So the precession of the equinoxes, which is shown here, is one of the main forcings of climate. The equinoxes are the points, are the places where the Earth, the plane of the equator of the Earth intersects the plane of the orbit of the Earth around the sun. These are the equinoxes, and they move like that. Well, this actually is part of the interlude for Olavista, so I'll skip it. The last one is this, the calendar that had to be modified in 1582 to adjust it to the seasons, and the current calendar, the year has 365.2425 days in a year, and this is 365 plus 1 day every 4, right? Those we add 1 day every 4. Then, if the year is multiple of 100, we don't add that day. But if it is a multiple of 400, we do add that day. And that way, we keep the calendar synchronized with the seasons. And that's the end of the interludio for Olavistas. Okay, let's go back now to. In 1941, this astronomer, Serbian astronomer Milutin Milankovic, proposed that the three main cycles that we've discussed of the Earth's orbit is missing here, determine the climate. And what are the three cycles? Well, it's the precession, and the period of precession is between 19 and 24,000 years. Then there is a nutation that changes the inclination of the orbit of the axis and therefore really has an effect in insolation that has a period of 41,000 years and varies between 21.5 and 24.5 degrees. Currently it is 23.5 degrees inclination of the axis. And then is the eccentricity of the Earth's orbit that according to Milankovitch varies with periods of 100,000 years and 413,000 years. So these three cycles, and we will use this, well, this is the standard nomenclature that is used for these periods, would explain the ice ages. Notice that this 100,000 years comes up in the duration of the ice ages. So here we have, at the beginning, we had then clearly this period of 41,000 years, which is the inclination, the tilt. And then, for some reason, it changed to 100,000 years, and we will see why that happened. Now, you can take this time series and do a periodogram and find out, Fourier transform or whatever method you use for finding periods in time series, and you find 100,000, 97.5, 100,000 year period of the glaciations, which is the strongest one, the strongest signal here. Then you have the 41,000 years of the nutation. Then you have the precession is here in 2 peaks, and then there is a little one which probably is not significant here at 11,000. So, how to explain that? Well, it turns out that with the modern people, the people that work in celestial mechanics today, can calculate these things, right? They take the equations, they expand it in a Taylor series of 100,000 terms. They retain the 50,000 or 25,000 terms, which are more relevant, and they solve these equations. And they're able to predict all these variations. Now, they cannot predict it very far into the future because these n-body gravitating systems are chaotic or become chaotic. But up to, they say, up to 4 or 5 million years, they can. The calculations are accurate, and in fact, all we need is a fraction of that. So this is the calculated variation. And so what you have to do is, of course, you have to take the Earth, the rotation of the Earth, and then calculate all the torques due to the Sun, to the Moon, to Jupiter, to Saturn, to all the planets, right? It's a complex calculation, but it can be done. And if you want to have these results, they will send you a polynomial with, I don't know, 250 terms that you can use to predict this values in the future. So the inclination is here, epsilon in degrees between 21 and 25 is the scale. This is the eccentricity. Notice the eccentricity varies between 0 and 0.05. 0 and 0.05. So here I have drawn examples of eccentricities. This is an eccentricity of 0, and this is an eccentricity of 0.2. So it's almost circular. The Earth, the orbit of the Earth around the Sun is almost circular, but it's, we know it's elliptical, but here's the calculation. The precession is the sine of the angle of precession, sine omega. It goes between -1 and 1. Then is the product of the ellipticity times the sine of the precession, because if the orbit was not elliptical, but it was circular, completely circular, this would not have, the precession would not have an influence in the amount of radiation that falls on the Earth. So this is a product of this times this, and it looks like that. And from all these values, they can calculate the amount of energy falling on Earth on average in the summer at 65 degrees north latitude in watts per square meter. Okay, so they use this and they calculate how much energy is falling on the Earth, and you see that this is this polynomial, let's call it, and this is what's driving the climate, right? The amount of the Earth radiation that falls on Earth. Sorry, solar radiation that falls on watts per square meter. It's about 500 watts per square meter at 65 degrees north in the summer. Okay, so this is the main product of this calculation is the insolation. Now here's the record of the climate plotted on top of that. Okay, so what happens if now we take the insolation polynomials and we do a periodogram just like we did for the climate record? Well, we find a signal at 19, a signal at 24, a signal at 41, but there is no signal at 100,000. Okay, so this Milankovitch theory does not explain the ice ages, and understanding the ice ages is important because the ice ages are the most important climate variation that we have experienced in the last million years. Now, this is just a plot to show you that the CO2, the amount of CO2 in the atmosphere, and the temperature go hand in hand. So indeed, one can use the atmospheric CO2 as a proxy for the temperature. This plot is interesting because they gathered data from a lot of places, and you see that the southern hemisphere starts reacting. The yellow line is the CO2, and the colored lines are as the temperature starts reacting earlier. There's a phase difference between the northern and the southern hemisphere. But the important thing of this plot is that to know that we can use, when we talk about climate change, we can use CO2 or temperature, and it's basically the same thing. Now, there is this mid-oceanic Atlantic current called AMOC that really is what does the transportation of heat from the poles to the equator and from the equator to the poles, and maintains the global balance of heat on Earth. And this current is essential, and since you see here that the Panama Isthmus emerged, then the current was forced to go this way instead of going that way as it went before. Now this is another plot. I will skip this about the Polynia and go back to the ice ages. In order to talk about the ice ages, I have another interlude. This is for aficionados of nonlinear systems. In a nonlinear dynamic system, you have the stimulus and the response, E and R. And if the system is linear, then the response is just proportional to the stimulus, and these are some examples for C equals 2. If it's quadratic, then it replies like this. If it's exponential, then it goes much faster, right? From 1 to 3, it goes from 20 to 2000, whereas here it went to 2 to 6. And if it is chaotic, means that if you change the input by a very, 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 very infinitesimally small amount, the response of the dynamic system will change completely, right? So here in this cartoon example, you change it by so many 10 to the minus 10, and it gives you 1,000. If you change it by 2 times 10 to the minus 10, it gives you 0.1. This is a chaotic system. Now, we now think that this 100,000 year glacial period oscillation that we see in the climate record is due to some kind of chaotic response of the climate system to the Milankovitch forcings, to the astronomical forcings. And how does it work? Well, even the simplest systems, like a double pendulum, for example, can develop chaos after just a few orbits. Here's an example you can find in the internet, real examples where they've done it with the real pendulum. This is a numerical example, but you see already that the trajectory which is being described by the second mass in the pendulum is completely chaotic. It goes all over the place. The other one just oscillates within its well-defined orbit, but the end of the pendulum describes a completely chaotic orbit, such that if you change the initial conditions by just a little bit, it will describe a completely different orbit. Now, if the orbit gets trapped around some specific points, and it's orbiting like this, then it jumps like that, then it jumps like that, as you perturb it a little bit, then the attractor is called, no, sorry, these points are called attractors. The orbits get trapped around an attractor, then you perturb it a little, it jumps to the other one and goes back. This is the famous Lorentz attractor. Now, if the shape that the orbit describes around an attractor is fractal, which means that it has the same structure independent of the scale magnification that you look at it, then this is called a strange attractor, fractal orbits. And strange attractors have the most beautiful shapes, like this one, for example. Now, if you write simple models for the climate, for example, this is the Salzman and Marsh model, where the terms are the Milankovitch forcing, which is what we saw before, that polynomial of 61 north in the summer, m, which is here, the volume of ice, the amount of CO2 in the atmosphere, and the North Atlantic deep water formation. We didn't talk about this but this is another of the parameters you put here. You put them in the equations, you solve these equations, and what you find out is that the climate is the response of the atmosphere to the astronomical forcings, which we call the climate, is in a non-chaotic attractor, in a non-chaotic straight attractor. What does that mean? It means that instead of being sensible to a very small perturbation that makes it jump to another configuration, it has a basin of attraction. Within a certain basin, it is stable, so that if you perturb it a little bit, it will come back. It will come back and stay stable within that range. It is not chaotic, but it's almost chaotic. It's a non-chaotic strange attractor. What causes this 100,000-year response to the Milankovitch cycles. And here's an example of some solutions. Here is again the temperature of CO2 record in the glaciations, the blue points of the data, and this is the model. Now, in order to adjust this model to the data, in order to do this adjustment, it was all of the parameters that you saw in the previous equation had to be adjusted very finely. So that's one thing. The second thing is that the fit is not very good. It just reproduces a period, but not more than that. So you cannot use these models. You can use these models to sort of theoretically understand why the Earth responds with a 100,000-year period to the astronomical forcings, but you cannot use it to predict anything. They don't have any predictive power. They just are in that sense, they're toy models. The other thing one can do is use the climate of the past, for which we know because we can calculate the Milankovitch term, which is this one here, and see whether it matches some of the records of the past climate. So you look at this figures and say, well, this one looks remarkably similar to this one. Or this one, for example, this one looks very similar to this one. How do the astronomical forcings of that time look like? And you align the curves. This is for one of these periods. You align the curves, you align the precession, you align the obliquity, you align the the summer, the amount of insolation, and then once you have it aligned, you take the recorded history, what you saw in the climate, which is this dotted line, and you compare it to the observed. In this case here, for example, you compare it to the observed CO2 concentration in the atmosphere, right? So we have aligned this curve, so we assume, because they match exactly, that the forcings then and the forcings now, the astronomical Milankovitch term, the insolation per square meter in the pole, are identical. So we remove the astronomical signature. And then we compare the records of CO2. And this is today. So you see, this is then, I think it's 470,000 years ago that period was taken. And this is what we observe today. And there is a departure of 290 versus, what do we expect here? 240 more or less, 40 parts per million of CO2. If you come here and you compare, you translate that to temperature, it's about 2 degrees, right? 40. So this exercise of removing the astronomical influence and leaving just what we see indicates that we should probably already be entering in the next glacier period, temperature going down slowly and going back into the glacier, and instead we see that the temperature is going up and the CO2 is going up. So we are way off what we would expect from the natural weather change if this was only due to natural causes. In fact, if we look at the records, this is the pre-industrial era, 1,000 years ago, 2000, 1000. This is the Industrial Revolution. The CO2 went up exponentially, and it reached 400 parts per million in 2013, and today is about 415 parts per million. Okay?
Sorry.
Yeah.
How is calculated this concentration of CO2? Is determined with the ice?
This one?
Yeah.
Oh, you mean the past one or the current one? The concentration is taken from real measurements in the atmosphere. Now there are places where they are measuring this. This is not so old.
But in the past?
Oh, in the past they used various techniques like sediments but I don't think the ice has the resolution. But there are many different ways of inferring this. The geologists know how to do. And then, of course, now it's measured by an observatory in Mauna Loa, sorry. So we know that. So notice that the concentration has gone from 280 to 400. So you ask the question, well, the models don't work. Doing this trick of matching the astronomical forcing doesn't work. What else can we do? The other thing we can do is we go to see in our records of the past, can we find periods in the past when the concentration of CO2 in the atmosphere was this high as we have now? It turns out that the answer is yes. And there's a lake. The lake is called El Gigitkin. It's in Chukotka, which is the sort of the westmost part of Siberia. And this lake Here it is. It was formed by the impact of a meteorite or an asteroid. Another one just hit there. What? Okay. And it's located here and has never been under a glacier. And the history of the climate on the Earth down to millions of years is recorded at the bottom of the lake in the sediments. And it turns out that these sediments are sediments of trees, seeds, leaves. So there is an area of geology that they specialized in determining the ages of fossil trees, and this is how they measured the various parameters. And here it is what they found. This plot is horrible, isn't it? So let's start see the time. This is thousands of years ago. So this is 3.5 million years ago to 2.2 million years ago. This is the temperature. Now let's first go to the concentration of CO2. The concentration of CO2, which is in this scale here, was at that time, 3.5 million years ago, about 400 ppm. ppm is parts per million, so that's 0.04%. This is the concentration of CO2. What was the temperature? Well, the temperature in those days, if we read these graphs here, around that part here, was up between 6 and 8 degrees centigrade higher than the temperature today. What was the ocean level? The ocean level is recorded here, and you can see it. 0 is the current value, was about between 10 and 15 meters higher than today. So if we use this as a proxy for the past, we see that at 400 parts per million in the atmosphere, now we are more than 400 parts per million, the prospects are intimidating. Now, look at this plot. This plot is the end of the last glaciation is here, and then this is a long summer. Down here, this is the exponential rise that we've seen. And if you see this level of CO2 is 180. At the end of the long summer before humans started intervening was 280. So the change between glacier and peak of the interglacier is 100 parts per million, roughly 100 parts per million. Now we have increased it from 280 to 420, so we've added another 140. So the impact of what we've done to the atmosphere as humans by putting all the CO2 in there is bigger than what a glaciation does. So we expect the consequences to be of the importance of a glaciation. Well, this is just, we saw this. This is a magnification. That shows that currently the CO2 is increasing at 2.5 parts per million per year. Okay. So here the cartoon says, look at the bright side. The Dow Jones is up 30% this month, and indeed we are burning the Earth. This is you've seen this plot. It goes is everywhere. It's the temperature anomalies on the Earth in this period, 214 to 218, compared to this baseline. And you see up here in the northern hemisphere has gone up already by 2 degrees. Here Brazil is a little bit worrying. There is this hot spot in front of Uruguay, which is ruining a lot of the ocean-based economy in that part of the world. And here is a bit colder. Well, that's what's happened. to the Earth. Now, I would propose that we stop here. The rest of the issues that we can deal with in questions. Is that okay? Do I have a? Do I have an? Let me put up an ending.
Thank you for your
Thank you.
And I have a question because you focus on CO2, but what about methane? Because methane also, I think it's a big issue on that model, don't you think?
Yeah, methane. The people use CO2
Yeah.
Generally, but the main greenhouse gases are these three: the CO2, there, CO2, the NOx, in particular this nitrous oxygen, and methane. The interesting thing was that in between 2000 and 2008, methane sort of seemed to have reached a plateau and was not increasing anymore. But in 2008, it started going up again, just like CO2. Now this rugged profile is because summer and winter changes, and same here. So methane is again a problem. Methane is 30 times worse than CO2, and is going up. Part of this going up has to do with agriculture, and part of this going up has to do with fracking. It turns out that fracking, which is the dissolution of rocks by high pressure chemical jets, releases a lot of methane into the atmosphere. I mean, the process is not tight. Part of the methane is not captured and is released in the atmosphere. So the methane is going up again, and it's a problem.
You can put the plot that is the temperatures with years that do. I believe, yeah. In this plot is the oxygen isotopic.
Yes.
Yes, and you can look that the difference is increment in the. I can look that the difference is in increment.
Yes.
In the years, and also in average, the temperature is decreasing.
Yeah.
In average, but
yeah.
it's, I don't know. For me, it's strange because if you have how I can look the greenhouse is I wait that by the effect of greenhouse increment the temperature, but you can look in this plot that the temperature is decreasing of the.
Yeah. Let me see if I remember exactly how it works. The benthic isotopic ratio is what is measured in the shells of micro organisms that die and the shells go down to the ocean. Now, when the temperature is higher, there's more CO2. The ocean is more acidic. Let's see how it works.
Because I don't know. I look here that the temperature is.
The temperature is going down. When the temperature goes down, these little creatures in the ocean are happier, and they form in bigger amounts. But this is the isotopic ratio. It has to do with basically with the isotopic ratio of water for the oxygen that they fix with the carbon. But I don't remember exactly how does this is done. The geochemistry is done there.
And the other question is that in the case of the Milankovitch.
The Milankovitch cycles.
Yeah. I don't know if this model consider the evolution of the stars or of the sun, because Because I look that only consider change in eccentricity, inclination, and
Yes. No, it does not. I don't have the slides here for the evolution of the sun, but the sun in the last million or 2 million or 3 million years hasn't evolved very much. However, there was this period in the Middle Ages, which is called the Maunder period, when for 100 or 200 years the sun did not have any spots. Right? That was because the Chinese have been looking at suns, counting spots in the sun for thousands and thousands of years. So we have a very precise record of the number of sunspots, historical records. And during this time in the Middle Ages, that was very cold, very known, and you have these paintings by the Dutch painters where everything was frozen, and the sun did not have any spots for a long period. So the 22-year cycle, or the 11-year cycle of the solar dynamo was, for some reason, interrupted. And that affected the climate. But it's details that are not included in any models of stellar evolution that I know.
So, as we think that this process is already going on, it's triggered, and what can we do if now we stop at all cars, all CO2 emission? Do you think that it could be some kind to stop this greenhouse effect, or is better we think to move on to another planet?
So this is the pathways of the IPCC predictions, depending on what the evolution of the CO2 in the atmosphere is going to be. So this is without nothing, business as usual. This is with the current pledges made by the Paris Agreement. This is now. And these are the pathways that we need to maintain the temperature below 2 or 1.5 degrees centigrade. People are now talking about we've already passed the turning point, exactly. So they say we live now in an overshoot period. We've already passed, and we will need to extract carbon from the atmosphere in order to meet these pathways. It is this plot. Now, so people are now working on ways of reducing the CO2 from the atmosphere, what they call the negative carbon emissions or negative carbon economy, and there are many ways of doing this. But the difficulty is that in order to compensate for the overshoot that we produce here, we need to remove 20 gigatons of carbon per year from the atmosphere. The current estimates of, I think I have one. Yeah. So these are the technologies, and I don't know if you can read this thing. I don't know if you've ever participated in one of these review panels where one has to review a technological project, and the jargon is the technology readiness level. So they want, when they go to launch the shuttle, you have to pass the technology readiness level 7 in order to deploy. And so this is now the technology readiness level of these various projects. So direct air capture is one thing you can do at a cost of $500 per ton. You need to capture 20 gigatons per year, so you can calculate how much that costs. So the challenge here is to reduce this to $50 per ton. But the experts don't think that's going to go further than that. Now there is a revolution happening in agriculture too. It's interesting, the things that are happening in agriculture in terms of the what they call it now. Each plant has a sensor. They call it precision agriculture. Smart agriculture, precision agriculture. They are now. There's a big revolution happening there, such to make sure that in agriculture you don't degrade the soil, because if you degrade the soil cannot capture any CO2. So there's a big change here. There's also forestry. Well, I am afraid I'm biased here. I follow in these subjects, I follow what's going on in the United States, in the US. Yeah.
Why there was such high concentration of CO2 during the Pliocene, and how the CO2 was removed to the low levels as at the beginning of
the temperature in the Pliocene was much higher. There was.
But why?
Because the temperature was the Earth temperature has been coming down, for the past millions of years, and there was no ice in the North Pole. There was very little ice in the South Pole. The oceans were hot, and the oceans. The ocean is the biggest reservoir of CO2 that we have. The ocean stores most of the CO2 is in the ocean. So with the hotter oceans, because the carbon gets fixed in the shells of these little animals. But when the ocean is very warm, and there's a lot of CO2 dissolved in the ocean is acidic, and these guys cannot form their little shells. So they don't fix as much oxygen. So the oxygen has released all of the CO2 that it can store. And that's why in the Pliocene it was higher, because it was hotter. Now, maybe it was hotter because the CO2 was higher, or maybe it was higher because it was hotter. That is a question that, from that plot I showed where there is this big phase between the northern and southern hemisphere, we don't really know whether the CO2 was first or the temperature was first.
Yes. Yesterday I asked the same question. Is someone in the world thinking about the possibility of we are losing our atmosphere? I mean, properly losing. Just gas going out of the atmosphere. I believe that someone have maybe done the calculation of escape velocity and so on for a small particle,
I have
for
a
a
picture.
small atom. Yeah?
Let me show you a picture that I really like. Maybe if I can find
Because this cooling is very, very true.
This is our atmosphere. It's just a little skein around the Earth. It's so tenuous, so small, right? It's just a little skein of the Earth. It's what we astronomers call a runaway effect. So a runaway effect happened in Venus, where the original concentration. Today, Venus has 98% CO2 in the atmosphere. We have 0.04%. But this was a runaway process. Something started and it fed up on itself, and it just whoop. And probably Mars was the inverse. Mars lost its atmosphere again for some runaway process. So since the climate is a non-chaotic, strange, it's the climate is the, how can I put it, is the answer of our atmosphere, or not only the atmosphere actually, because the ocean is very important, is the answer, the response of the Earth to the Milankovitch forcings. It's in a non-chaotic strange attractor, so it's quasi-chaotic. You can, it is subject to turning points, to tipping points, right? So if you perturb it too much, it will jump and go someplace else. Right? It has a basin of attraction, so that brings it back, not like a chaotic system that you perturb it infinitesimally and it jumps. Here you have to perturb it more, a little bit more, but not much more, and it may jump. It may jump. If it jumps, where is it going to settle? It may be that we're losing it in the atmosphere. I don't exclude it, but since our models are so lousy, we really don't. I mean, but what is clear is that the response of the Earth to the perturbations is incredibly nonlinear. It's almost chaotic. I mean, more nonlinear than chaotic you cannot have. But this is almost chaotic. So it could be, well, we
But we have to consider a magnetic field protecting the Earth atmosphere, no? Against the solar wind, something like that, that could remove the atmosphere.
in the case of Mars.
Yeah.
In the case of Mars, in the case of Mars, yes. In the case of Mars, it could be that the solar wind just blew the atmosphere away.
So that we can shut up the climate skeptics, how can we be sure that the rise in the CO2 and temperature are not results from the chaotic behavior of our climate system? Or can we be sure? And if so, to how much degree? I mean, how can we differentiate the fact that the CO2 and the temperature levels are rising from the natural chaotic behavior of our climate system and from the anthropogenic contribution?
Well, what we saw is that the natural oscillation, which is a response of the Earth to the perturbations, makes it go from 180 to 280, down to 180, up to 180. This is what's been happening for the past million years. Now, all of a sudden, after the Industrial Revolution, we saw that it jumped to 420, and it's not, we don't know, it's going to oscillate back, but this is way out of, it's much more, it's 50% more than the glaciation. So it's a big perturbation. And we have no idea how the Earth is going to respond. The people that do the modeling for the IPCC, which are global circulation models, they're not climate models. They are climate models, but they don't go to this level of chaotic response because we don't know how to do it. They claim that for as long as we keep the CO2 below 450, we're okay. If we keep it below 450, we're going to have an increase in temperature of 5 degrees in year 2000 and 2100. But you see that this sun jump is something we've never seen before. So I would not think it's a natural oscillation, but it may be a jump.
You know, it's because a lot of skeptics, if I of course disagree, and say no, but this is because of the natural.
Yeah, but that's what we saw. We saw the nature.
Yeah, but I think it's. I mean, are we gonna gamble with this? Are we gonna take our chances, even if it's something?
What the skeptics say, oh, this is 0.04%, right? It's changed by 0.01%. This is nothing. 0.01% is a glaciation, right? So it's, if you perturb the CO2 by 0.01%, you get a glacier period or a non-glacier. So it's big. It's a huge perturbation. It's not. I would not take my chances. I'd rather spend how much did we calculate? 2 trillion. 2 trillion a year is a lot of money. It's a lot of money, but it's just the equivalent to the energy sector. That's how much money is involved in. It's not so much for the, and it's industry. It will give jobs. It will give, right. So.
Thank you very much.
No, but is there an explanation for the longest summer? Because it seems that it's not something periodic, something that happened that time, but It's not cyclic.
The long summer?
Yeah.
Oh, it's the interglacier. Oh, why the summer is long? There are discussions about that. There are some people who say that already when agriculture was invented, and even before, there was methane released into the atmosphere because of burning forests and clearing land for agriculture, and that already altered the climate. But we don't have it doesn't seem to me that this current interglacial period is longer than any once in the past. Although, as you saw in that plot, the temperature is no longer going down, it's going up. So it's called the long summer, not the longest summer.
So let me open the road to psychology then.
Oh dear.
So why do some people insist in denying climate change, and how that idea is spread?
Look, there are people who have vested interests, right? If you own an oil company and all your value is in the oil that you have, right? It's none of the oil that you're selling, it's the oil that you have in your pits. You don't want somebody coming and tell you, look, you're going to have to leave that carbon there because if you take it out. So there is that part. There is a part that people are spreading fake news to confuse people, right? And there is a part that our brains sort of, since all of our behavior is against our best interest, right? So we cannot continue to drive because we're damaging the earth, but we drive. And we cannot continue to eat hamburgers because we're damaging the earth, but we eat hamburgers. And all of these things, then our brains at a certain point simply block it and take it out of you. So you continue to drive, you continue to eat hamburgers, you continue to do all of these things, take airplanes to go places, because your brain has closed that chapter out of you. So this is a natural mechanism.